now we're going to be moving on to the transformations of logarithmic functions. So we're going to get into the graphing. I do have one correction from the first video. It's actually only section 2 that we're going to deal with the graphing of the logarithms. We're going section 3 and 4. I'm going to talk about the equations more. So since logarithmic and exponential functions are very closely related, we can make some really nice recall to this information. So if we had the equations y equal 2 to the power of x and 1/4 of it, oh, that is definitely a typo. That should be a y equals 1/4 of the power of x. We have to determine that these exponential functions, whether they're going to be increasing or decreasing. Now, super quick, since our base here is greater than 1, this would definitely be an increasing function. Whereas our base here is in between 0 and 1, it would be a decreasing exponential. So for the increasing exponential, that's really nice and easy. Now we can do it relatively simply. And actually, I'm going to put it in purple. I know that 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, so on and so forth. Then we just be at 1/2, 1/4, 1/8. The exponential function is going to look generally like this. So our 2 to the power of x is going to look like that. Now I'm actually going to sketch this 1/4 as well. So I know that power of 0 is 1. Let's see. 1/4 power of 1 would be a quarter, and then a 16th, and so on. But 1/4 to the power of -1 would be 4. 1/4 power of -2 would be 16, which is way off our grid. So I'm going to try my best to sketch this one. So this exponential is looking like that. Again, that just ties back to our first unit and all that. But now what we're going to do is we're going to sketch their inverses. Now remember that to sketch an inverse, either we switch our x and y and then we solve, and I'll show you with the equations what that actually looks like. As well as there's the other alternative of switching our x and y coordinates. So this point of 0, 1 would become 1, 0. The point 1, 2 would become 2, 1. The point 2, 4 will become 4, 2. The point 3, 8 will become 8, 3. Now again, just where I'm getting those points are, this point would be 2, 4. This would be 3, 8. So literally switching the x and y, that would just become 8, 3. And by looking at it, the inverse would generally look something like this. Now, that's not the only way that we found out equations or found out how to graph inverses. The last one that we had talked about is it's always going to be a reflection over the line y equals x. So the exponential y equals 2 to the power of x is that purple graph. The inverse of it is that red graph. And before we get to the inverse stuff, I'm just going to do a sketch on this one for this inverse. So again, if we're looking at points, this is the point -1, 4. So the opposite of it will be 4, -1, or -1. just switching the x and y. This point, 0, 1 would become 1, 0. Now, this one is a little bit trickier, but through lots of practice, I know that our graph actually looks like this, which is still actually a reflection over the line y equals x. It looks kind of difficult to see it, but it is there. Now, just so that you are fully aware, these ones are our big, these are going to be the big focus that we're going to be doing with the graphic. We're not going to be dealing with this 1/4 to the power of x and all that. But where I want to tie this into is the idea that if our equation is y equals 2 to the power of x, the inverse would be written as x equals 2 to the power of y. So that would be the new exponential equation, but we don't like doing that like that way. So in order to solve for our y, what we have to do is rewrite it in the logarithmic state. And we're going to do a little bit more of this this equation bit in our next sections. But what it would look like is it would be y equals log base 2 of x. So that's what our red graph actually is. This is the equation y equals log base 2 of x. Similarly, on this one, it would actually be y equals log base 1/4 of x. Now again, just kind of literally in recording, so you can come back to it and call me on it if I do. I'm not going to give you these decreasing functions for sketching inverses of, like this log base 1/4 of x. It's not going to be really nice. I'm going to stick with our bases being greater than 1. So that they're going to look generally like this, of course, with other transformations. Now, the graph of a logarithmic function y equals a log base c of b bracket x minus h. Oh, I definitely forgot another bracket. I'm just going to make that red so I can see that better. Plus k can be obtained by transforming the graph y equals log base c of x. Now, just one further note. Our general transformation of functions is what y equals a f of b x minus h plus k. Notice how our transformations all are in the exact same locations throughout. If we tie it into our exponential, y equals a c to the power of b x minus h plus k, our transformations don't change. The only difference is that it looks slightly different. So our exponential function, it's still a, b, h, and k. Our logarithmic is still a, b, h, and k. The only difference is kind of what that c value is. And that's what this last little note is. So that c value here, the only thing that does make these transformations a little bit different than exponential transformations is that we need to actually flip the exponential x and y values before our transformations. Now, I'm just going to say it right now. It's a little bit difficult to try and get the points for a logarithm. But for an exponential, it's actually pretty easy. Without doing a whole bunch of work to get our logarithms, we can do our exponential relatively easy, and then we can do some transformations there. So let me show you what I mean. We're going to use transformations to sketch the graph of y equals log base 3 of x and y equals -2 log base 3 of x plus 4 minus 1. Identify the following characteristics, yada, yada, yada. So long story short, this is our logarithm. The exponential will be a y equals 3. Oh, wow. Y equals 3 to the power of x. It's just taking that base 3 to the power of x. Getting these points is really easy. So let's do that. If we choose some points, what the heck? All right, -2, -1, 0, 1, and 2, we can find out the points for this exponential really easy. 3 to the power of -2 is 1/9. 3 to the power of -1 is 1/3. 3 to the power of 0 is 1. 3 to the power of 1 is 3. 3 to the power of 2 is 9. As soon as we have those points, though, in order to get the logarithm, since the exponentials and the logarithms are inverses of each other, to go from the exponential to the log, switch the x and y. So instead of -2, 1/9, it's 1/9 to -2. Instead of -1, 1/3, 1/3 -1. And we continue. Oh, sorry. That should be 1, 0. Three, 1, 9, 2. So the points for the logarithmic graph would just be this. If we're going to transform it into this -2 log base 3 of x plus 4 minus 1, we apply our transformations. Now, let's just do a little verbal exercise of what this means. -2 in front is a vertical stretch. So the 2 means it's a vertical stretch by a factor of 2. The negative, since it's dealing with our y's, would be a reflection over our x-axis. This x plus 4, which is on the inside, means it's going to be moving left 4. And that -1 means it's going to go down 1. So if I want to deal with I have this space here as a mapping notation. The -1 is applied to our y's, or sorry, -2 is applied to the y's. So the only thing applied to our x's is that +4, which means it's actually our x's subtracting 4. Our y's are going to be multiplied by -2. And then we're going to subtract 1 from them. So x subtract 4, 1/9 subtract 4. So if I want to get to a nice point, let's see, that should be -3 and 8/9. Oh, sorry, erase that. Yes, I'm going with the hard numbers first. 1/3 subtract 4 would be a -30 and 2/3. 1 subtract 4 is -3. It looked like a 3. 3 subtract 4 is -1. And 9 subtract 4 is 5. -2 times -2 is 4. Subtracting 1 is 3. Oh, just before I go any further, I'm just going to double check my work here. Yep, I think I'm still good. -2 times -1 is +2. Subtracting 1 is 1. -2 times 0 is 0. Subtracting 1 is -1. 2 times 1 is -2. Subtracting 1 is -3. Negative 2 times 2 is negative 4. Subtracting 1 is negative 5. So let's take a look at what these graphs would look like. Now I do actually want to graph both of these. I do want to graph the natural log, or sorry, just the logarithmic base 3 of x, and this negative 2 log base 3 of x plus 4 subtracting 1, just to see how this has been transformed. So 1/9 negative 2 puts us there. 1/3 negative 1, 1, 0, 3, 1, 9, 2. So our logarithm dot, 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 dot. So y equals the log base 3 of x looks like that. Now it does have some certain characteristics to it. For example, before I even get to the other one, let's talk about the asymptote, the domain and range, and the x and y intercepts, if they exist. So the asymptote, in this case, is no longer a horizontal like we're dealing with the exponentials. It's a vertical asymptote. This one. So for y equals log base 3 of x, the vertical asymptote is x equals 0. The domain, which is the next thing on that list, is x such that x is greater than 0. The range is y such that, well, it's going over all real numbers. So y is an element of the real numbers. And this has an x-intercept of x equals 1. But because of our horizontal asymptote being that y-axis, we have absolutely no y-intercept. So now let's look at this y equals negative 2 log base 3 of x plus 4 minus 1. So if we sketch this, negative 3 and 8/9. Negative 3 and 8/9, and then 3. It's negative 3 and 8/9. Be about there, and 3 is going to put us about there. Negative 3 and 2/3. 1. Negative 3, negative 1. Negative 1, negative 3. And 5, negative 5. So it's a little bit harder to see this one. If you connect the dots, or try your best to connect those dots, our new graph looks like this. So now let's take a look at what kind of characteristics we have. Our vertical asymptote has now shifted. Instead of being at 0, oh, didn't grab the right thing. Instead of being at 0, it's all the way at negative 4, which, actually I'm just going to write that first. Vertical asymptote, x equals negative 4, because it has moved left 4. This logarithm has moved left 4. Our domain x such that x is greater than -4. Our range, it's still going over all real numbers, but there is definitely a note to make about that. I'm actually going to leave the x-intercept for a second. And actually, our y-intercept, maybe we can do those. I'm just going to make a quick note. So you can see in here, this log base 3 of x is actually an increasing function. It's actually going up as it goes from left to right, which still fits exactly with that 3 to the power of x, that exponential being our base being greater than 1. It's still an increasing exponential, and its logarithm is also increasing. But you can see on this green graph, this -2 log base 3 of x plus 4 minus 1, it's actually something that goes down. And the way that we can determine that is just by that equation. That -2 means that this increasing function has now flipped over the x-axis to, instead of being an increasing function, now it's become a decreasing function. It has absolutely expanded or vertically stretched by that factor 2. It might not be the easiest to see, but if you're looking at the points, each of these points here, so this point is at -2, this point is at -1, then 0, then 1, then 2. But if you're looking at the points on this green graph, it's at 3, then 1, then -1, then -3, then -5. So it actually has, instead of being a space of 1 in here, each of these spaces here is actually doubled to be twice as big now. Kind of a little tidbit to help you see things a little bit better. Now, just before I do some calculations for x and y-intercepts, now I'm going to show them algebraically. Just this subtract 1, it's kind of hard to see with logarithms that it has moved down 1. So that's why using this mapping notation is going to be a really crucial skill. Just, you do it, and as long as you've done your points correctly, you're set. Some of these different characteristics, like that reflection and that moving left 4, for sure can be seen, but moving down 1, yeah, it's really hard to actually see that. All right, so if I want to find out my x-intercept, this is going to be something that does take a bit more work, and that's why there is a whole bunch of space here. In this equation, well, actually, sorry, in any equation, you can always find out x-intercepts by setting y equal to 0. So if our equation is y equals -2 log base 3 of x plus 4 minus 1, all we have to do is set y equal to 0. -2 log base 3 x plus 4 minus 1. So now we're going to have to solve for what the x is. And there, it's actually really nice to do, because I just have to add the 1, because I want to try and isolate this x value. I want to try and get it by itself. So we get 1 equals -2 log base 3 of x plus 4 divided by the -2. So we have -1/2 equals log base 3 of x plus 4. Now you're gonna like this and hate this next part. We're gonna use some whiplash. Take our base 3, to the power of negative 1/2, and it's going to equal x plus 4. So this is the part that you might groan about, but at the same time, it's really nice and simple. The part that is going to be really nice is use your calculator. What is 3 to the power of negative 1/2? Literally just type it in. If I type it into my calculator, I get 0.577. And that would just be x plus 4. So subtract 4. X equals negative 3.42. So our x-intercept is negative 3.42. Does that fit as best as possible? Absolutely. And just to finish this off with our y-intercept, I'm actually going to leave you hanging on this. Now, just so you know, the y-intercept is calculated when x equals 0. Yes, I definitely know that this is 2 parts of the equation. I just wanted to have lots of space here. So if you plug 0 in for your x here, y equals negative 2 log base 3 of 0 plus 4 minus 1. Simplify it further, we get negative 2 log base 3 of 4, subtracting 1. I'm going to leave you hanging here because it's hard to cut. You can't actually type this into your calculator without knowing one extra little bit of knowledge, which I believe I'm going to be covering in section 3. Yes, it is in section 3. So we'll come back to this, but just so you know, can see it's about negative 3.5. So I'm not going to be expecting you to solve for your y-intercepts. I might do a little switch around of some skills. I might have to re-record this video later, but that's a future me problem. And I don't mind recording some videos. All right. So one more note is that y equals ln of x and y equals log of x have the very same application. They both produce logarithmic functions. The big difference is that the bases are different. Remembering that e is the limit as n approaches infinity of 1 plus 1 over n to the power of n, which again is about 2.718281828, and I actually don't remember the numbers after that, but it's in your calculator. So if I talk about transformations to sketch, y equals 2 ln of negative x plus 1, let's identify some points. So y equals e to the power of x, I'm going to use negative 2, negative 1, 0, 1, and 2. When I go e to the power of x, again, you access that by pressing the second button. Then you press your ln button, which is right below your log button. So it's 2 below your second. So second e to the power of, if I type in negative 2, I get, I'm just going to go 2 decimal places, 0.14. Now when I actually do my stuff, I'm going to use a full value, but it's about 0.14. I go negative 1, I get 0.37. Obviously, to the power of 0 is 1. To the power of 1 is that 2.7. If I'm going to round to 2 decimal places, I'm going to keep it consistent, 2.72. And e to the power of 2 is a 7.39. The exponential is at e to the power of x. The logarithmic function, the natural logarithm, is this ln x. So instead of writing -2, 0.14, we're going to switch your x's and y's. Because it's always easier to find the exponential equation first and then switching our x's and y's. So 0.14, -2. 0.37, -1. 10, 2.72, 1, 7.39, 2. Now let's do some transformations. We can see that this 2 means it's going to be stretched by a factor 2. The negative here means it's going to be reflecting over the y-axis, because on the inside it's dealing with the x's, so we need to flip over the y-axis. And that +1 is not a +1. Because our b value is not isolated, we need to make sure we factor that negative out. So it's actually 2 ln of negative x minus 1. So that we can properly do our transformations. That's one thing that you have to keep on remembering. Now our x's, nice and easy. Our x's are going to be multiplied by -1, or technically, you can say it's the opposite on the inside. It's dividing by -1, but multiplying by -1 is the same thing. That subtract 1 means that yes, we are actually going to add 1 in this case. It is going to move right 1 unit. So in order for us to properly determine those characteristics, we need to have isolated that b value. And it's being stretched by a factor 2 vertically. So 2 times y. Now in this one, I'm going to actually do the y's first because it's way easier. I don't have to do any kind of hard work. These ones, I'm definitely going to have to do a bit more. Now, I know that this is e to the power of -2, so I'm going to put that in my calculator. So I'm going to transform this point. So obviously, this is actually 0.135335283. Very unlikely that you'd have to do anything further or anything too extreme with that, but I'm just doing it because I'm a geek. This x value has to be multiplied by -1, and then we have to add 1 to it. So it would become, to a decimal, go to 2 decimals, it would be 0.86, which probably is exactly what 0.14, yeah, actually, yeah, it would be. So it's not going to be anything different. Again, I'm just kind of doing the proper numbers just for mathematics' sake. If I go e to the power of the -1, that's that 0.37 or 3678. Let's see, I need to multiply that by -1 and then add 1 to it. I get 0.63, which would still be the exact same thing. This one's nice and easy. -1 plus 1 is 0. E to the power of 1 is that 2.7, multiplying by that -1, and adding 1 is a -1.72. And put to the power of 2, multiplied by the -1, add the 1, I get a -6.39. I guess none of these points would have actually changed if I didn't use those. And it doesn't hurt to know how to do math. Okay, so let's do a sketch of the ln x, and then we're going to do that transformation. So 0.14 -2. 0.14 -2 would put us there. 0.37 -1, about there. 10 2.721, 7.392, and our ln x function. Looks like that. So again, that is y equals the ln of x. If we do the negative, or sorry, the 2 ln of negative x plus 1, which would be 2 ln of negative bracket x minus 1, we're going to do these points. So 0.86, negative 4. 0.86, negative 4. 0.63, negative 2. 0.63, negative 2. 0, 0. Negative 1.722, negative 6.394. So this graph looks definitely a little bit different. If we connect our dots here, the graph looks like that. Now I'm just going to quickly discuss the ln x. This would be 2 ln of, I'm going to use the negative factored out, negative x minus 1. All right, so for ln x, our asymptote is x equals 0. Domain is all our x's that are greater than 0. Our range is all real numbers. X and y-intercept, well, there's no y-intercept, but the x-intercept is 1. For this one, we're not actually going to do this one algebraically because it's really beautiful to see, but our asymptote for this y equals 2 ln of negative x minus 1. Our vertical asymptote, we can see that it's actually approaching that 1. So it would be x equals 1. Our domain is all of our x's that are less than 1, because it actually has been reflected over that y-axis. So now into the real numbers. Our range, y's being an element of real numbers. Now, I'm not going to do this algebraically because it's actually pretty nice, but long story short, since both of our intercepts are, since it's going through the origin, our x and our y-intercept, is actually 0. So we can read it straight from the graph, and there we're good. We'll do some more skills with kind of solving those x-intercepts in our further section, but we'll deal with that then. So let's go on to our last couple of examples. So determine the equation of this transform graph. So basically going from this blue to red. I don't remember whether I got your stuff into color on this page or not. I apologize if it's not. I really did intend for it to actually be in color. This one says it's can be generated by stretching, reflecting the graph of y equals log base 4 of x. Write the equation that describes it. So really, it's nice and simple. Obviously, we can see that this has reflected over the x-axis. What does that mean? Since it's reflecting over the x-axis, the number in front of our logarithm would have to be negative. Our a value would have to be negative. Now, the only extra part is we can actually see that this space is 1. This space is 3. So it has been vertically stretched by a factor of 3. Log base 4 of X, and this is done. We've done lots of transformations, so I hope that this is relatively on the simpler side of things. If not, again, really what we're looking at is its points. We can see that this is a point that has not changed. So that's why I'm using this x-axis. Anything that's on our x-axis is not something that can actually be stretched vertically. And it says that it has to have stretched. So this point is not going to be able to stretch either up or down. It would stay the same. So to measure from this point to this point, it is a 1 unit space here. Whereas on this one, going from, again, that x-axis to a point that's given is a stretch of 3. So it's 3 height here, which means that our a value, instead of being 1, would be 3. So hopefully that helps fill all of that stuff in. Now getting into something that's a little more fun and kind of, again, more onto the applied side, is talking about, again, where the application of this stuff comes from. So welding is the most common way to permanently bind metal parts together. No guff. Welders wear helmets fitted with filter shade to protect their eyes from the intense light and radiation produced by welding light. The filter shade number n is defined by the function n equals 7 bracket negative log 7 over 3 plus 1, where t is a fraction of visible light that passes through the filter. Shade numbers usually range from 2 to 14. Lens shade number 14 allowing the least amount of light to pass through. And the correct filter shade does depend on the type of welding that you're doing. So a shade number of 12 is suggested for arc welding. What fraction of visible light is passed through the filter as percent to the nearest 10,000? So 12 is n. That's our shade number. Really, this exact example could have been done in our first section because it's really primary. 12 equals, now I don't actually like the way that this is written. I'm just going to rewrite it as negative 7 because this is just 7 times a negative 1. You'll see why in a second. It's just going to help with a lot of the manipulation. And then we're just going to solve for what t is, because t is a fraction of light. Subtract the 1, we get 11. This negative 7 log of t. For some reason I always do that. Multiply both sides by 3. So 33 equals negative 7 log t. Divide by the negative 7. Now I'm just going to leave that as 33 over negative 7. Actually, I'm just going to put negative in front. In fact, log t. And make one further note that any kind of logarithm, if you don't have that base, it's always implied that it's a 10, because our number system uses base 10. So in order to solve for t, we use our whiplash. 10 to the power of negative 33 over 7 equals t. So 10 to the power of negative 33 over 7. I might have to put some brackets on there to make sure it actually works. Zero point 0.00, that's the tenths, hundredths, thousandths, 10,000ths. Oh, maybe I have to switch that. Maybe I had to. 19307. Of course, because it's just a fraction of visible light. I want to know it as a percent. So if I multiply that by 100, it would be So I just moved 2 over 0.00 and 19%. So a shade number of 12 would give us only 0.0019% of light actually passing through, which is, yes, a very small amount, but because it's light, it still does give quite a bit of a shine, even if you are wearing a good welding helmet. If 50% of light passes through the filter, what is the shade number? Now this one is actually really nice. Since n is our shade number, again, I'm just going to leave this as a -7. 50%, well, t is of what fraction of the light? I'm just actually talking about 0.5 over 3 plus 1. This is actually wonderful because you're, in addition to any kind of logarithm being in base 10, you don't actually have to do anything further for this because your calculator already calculates everything in base 10. So you can actually type all of this straight into your calculator as is. So -7 multiplied by the log, which is just your button right underneath your second, log of 0.5 divided by 3 plus 1 will give us a shade number of 1.7, which will be approximately a shade number of 2. Because generally they don't go anything lower than 2, so our shade number is a 2. Just one little note though, the reason why we couldn't actually type this into our calculator before is because our calculator uses base 10 number system. But when I talked about this question back here, this has a base 3 number system. We can't do this with a base 3 until we learn one more skill from section 3. We'll just get to it. But with all of our stuff, it allows you to have some fun.